Hello everyone, my name is Usama Juma. I'm going to be presenting today alongside my group mates Ramnik Sandhu and Cody Simons. For our term project, we are going to be presenting on the topic of distance measuring wheel. So our agenda for this presentation will go as follows. First, I'm going to start off with the introduction, different iterations of the design, and briefly talk about our final design. Then Ramnik will continue on going more in depth on our final design, talking about the components involved and the circuit diagram. Finally, Cody will talk about our testing procedure, results and analysis of our design. The main objective was to ensure that this handheld instrumentation is able to measure longer distances unlike a ruler stick, and also has the capability to measure curved surfaces unlike a measuring tape. The group brainstormed many ideas, like using a traditional ball computer mouse mechanism, but to read distance instead of moving a cursor on a computer screen. Or another idea was a distance measuring wheel using a rotary encoder as can be seen in the picture slide. The group finally settled to 3D print the body and use an external sensing device to cut cost, and simply because it was what was most easily available. The basic concept of our initial design is a rotating wheel attached to a gear with a push handle. The gear teeth are meant to push on a finger counter device to track count of every gear tooth pass. The more the teeth, the more accurate the reading would be. So the group had to figure out a happy balance between increasing the number of teeth while giving clearance for the input button to be released after being pressed. For our initial design, the group 3D printed the blue wheel as a first draft prototype. Several quality of life tweaks has been added to the second thread design, like an extra front wheel for better system stability, and two rear wheels to make sure the sensor attached to the push handle stays in position relative to the rotating wheel for a more accurate reading. Finally, a cage was added to the top to house the finger counter reader. For our final design, the group had to change the sensor input from finger counter reader to an IR sensor due to supply chain issue. This ended up working better for us since it gave us more control over the system code. For example, we can now have different length unit readings. The way this works is the IR transmitter emits a beam of IR radiation which travels through the air until it hits an object. In this case, it would be the fins in the newly designed wheel. Also, for the final design, the gear and the finger counter cage has been naturally eliminated as can be seen on screen. Now, I'm going to hand it over to Ramnik to further explain the final design. Over to you, Ramnik.
Let's now discuss the working principles of our final design. The design is developed using an IR obstacle detection sensor. It converts number of turns into linear distance traveled by the wheel. The sensor's IR transmitter emits a transmitted IR beam and upon detecting an object or obstruction, reflects the beam back to the IR receiver. In our design, the IR sensor detects the various fins of the wheel. The code counts the number of fins that have passed the sensor and converts it into linear length. The linear distance L is the number of fins N times the arc length L. The total length is calculated and displayed for the user. The design consists of the following components: a rotating wheel, an IR sensor module, an Arduino Nano microcontroller, a 16 by 2 LCD display, an I2C 1602 serial LCD module, a breadboard, and jumper wires. The following schematic depicts the circuit diagram for our distance wheel. The wires in green are the grounded connections, and the ones in red are the power supply for the sensor, display units, and the Arduino. As a fin passes the IR sensor bulbs, the microcontroller counts it as a unit input and multiplies the arc length between the two fins to display a linear distance value. The final prototype of our design is as shown. It consists of a handlebar for the user to grab the measuring wheel. The sensor is placed between the fins, and as the user rolls the wheel, the distance traveled is displayed on the LCD screen. Currently, the Arduino requires a cable connection to a power bank or a computer. In future iterations, the design could be hooked with a 9-volt battery supply to make the wheels cordless.
Now I will discuss the testing procedure done in order to yield the results obtained from our IR sensor prototype. For the testing procedure, we decided to measure 3 table surfaces in the library, a table in the fabrication lab, a small side table, and a square table in room 105. Each dimension of each table were measured beforehand using a tape measure where the length and width were measured 4 times each and then averaged. This gave us an insight as to what each dimension of each table would be when measured with our sensor prototype. When using our distance measuring prototype, a line marker was established between 2 of the fins so that the IR sensor passed through the first fin as it was counted. This way it acted as a reference position where the prototype started at each time it measured a table dimension, and it was always at a position where the point was in perpendicular contact to the surface. When measuring each table, there were 2 trial tests performed, one for the length and the other for the width, with 20 samples in each trial. With each sample being measured and recorded, the time taken for each sample was also recorded as well. When all the data was collected for each dimension, an average was taken. These set of results show the data obtained from the measuring the Fab Lab table that was approximately 182.7 centimeters long by 75.5 centimeters wide. The first column in the table results show the number of revolutions the wheel turned as it rolled along the table's surface. From there, the number of revolutions was halved in order to know how many fins passed through the IR sensor. This was then multiplied by the arc length of 3.15 centimeters to give the overall measured dimension of either the length or the width. This set of data clearly shows that our sensor prototype is accurate. The orange line indicates the actual measured dimension by the tape measure, while the blue points represent the data collected from the IR sensor rolling along its surface. Any of the points that deviate from the actual distance represent that the sensor was moving either too fast or too slow when it was rolled along to measure the table surface. This next set of data results show the data obtained from measuring the library square table that was 106 by 106 centimeters. As you can see, the data obtained for the length is very close to that of its actual length as well as for its width. Any outliers below the orange line in both graphs are when we moved the sensor too fast, and any above it are when it was moved too slow in measuring the table dimension. And finally, these results show the data obtained from measuring the small study table that was 40 centimeters long by 31.4 centimeters wide. This set of data is consistent with that of its actual length. The measured length isn't exact because the IR sensor cannot read half of a fin, and that shows it in the first graph above. Any outliers in both graphs are from when the sensor was moved too fast in measuring the surface. There is some error that could be associated with the sensor prototype as it is used to measure distance. Firstly, there is some human error that can occur from the user. If the wheel is not moved in a straight line, it can generate an error in measurement. To mitigate this lateral movement, the device should be moved carefully in a straight line path. Also, there could be some slippage between the wheel and the measuring surface. This can be mitigated by wrapping some rubber bands over the wheels. And as we mentioned previously, moving the prototype too fast can also disturb the IR sensor and cause inaccuracy in measurements. Therefore, moving the wheel at a reasonable speed is recommended. And finally, there could also be some reset position error, which can be mitigated by using an automatic reset button in future iterations. Surface roughness also plays a role in error and can be accounted for by adding or subtracting the uncertainty value.
Let's now take a look at a video to demonstrate the working of our prototype.
Yeah, it was our project. Cool. Okay, yeah, that's good. And then we can put a hole outside, right? Oh, the hole is gone. Then this one. Yeah, and we can use that. We go to the, yeah, we can use this one right there? Yeah, yeah. Oh.
To wrap things up, we have successfully completed our project scope of creating a distance measuring instrument. In our future steps, we will quantify our errors and generate a plus or minus uncertainty value. We also plan on measuring another table, a curved surface, and a carpeted floor. And finally, we plan to complete the report that would act as a manual for the prototype. Thank you for listening. Please let us know if you have any questions.